In this video, we shall refer to cumulative distribution function. We shall focus on the cumulative distribution function of the standard normal distribution and illustrate an example involving log-normal random variable. First, let's have a review. For a random variable x with the density function f sub x, the cumulative distribution function of x, capital letter F sub x, is defined as follows. It is equal to the probability that the value of the random variable is less than or equals to small letter x. Recall that if x is normally distributed with mean equals to mu and variance equals to sigma squared, then the density function is given as follows. In particular, if x is a standard normal random variable, then we have mu equals to 0 and sigma equals to 1. Then we have the corresponding cumulative distribution function. We usually use capital letter Z to represent a random variable which follows standard normal distribution, and we denote its cumulative distribution function as phi x. The following are some properties of phi x. The first property is that for any value of x, the sum phi x plus phi of negative x is always equal to 1. The standard normal distribution is a bell-shaped curve, and it is symmetric at t equals to 0. From the formula of phi x, we notice that phi x represents the area of the region under the curve from t equals to negative infinity to t equals to x. So, it is the fielded area from the left to the place where t equals to x. Whereas phi of negative x represents the area of the region under the curve from t equals to negative infinity to t equals to negative x. Since this curve is symmetric, the area of this part is exactly equal to the area of the unfielded region here. Therefore, the sum of phi x plus phi of negative x is equal to 1. The following is another mathematical proof that the expression phi of negative x is equal to 1 minus phi of x. Please refer to it by yourself. In previous video, we mentioned the 68, 95, 99.7 rule for normal distribution. That is, there is a 68% chance that the value of the normal random variable is within one standard deviation from the mean mu. There is a 95% chance that the value of the normal random variable is within two standard deviations from the mean. And there is a 99.7% chance that the value of the normal random variable is within 3 standard deviations from the mean. For Z, which is a standard normal distribution, then the chance that Z is between negative 1 to 1 is 68%. And the chance that Z is between negative 2 to 2 is 95%, whereas there is a 99.7% chance that Z is between negative 3 to 3. However, it is difficult to find the value of this integral for other values of x. Instead, we refer to the table for the value for phi x. This table records the value of phi x, where x is the distance away from 0 on the right side of the tail of the standard normal distribution. Since the curve is symmetric, the table only records the value of phi of x, where x is a positive value. In case we wish to find phi of negative x, we will use the fact that phi of negative x equals to 1 minus phi of x. For example, the value phi of 1 is equal to 0.8413, whereas to find the value of phi of negative 0.83, we first use the formula 1 minus phi of 0.83. Then we observe from the table that the value of phi of 0.83 is equal to 0.7967. So, phi of negative 0.83 is equal to 0.2033. There is no need to have a table for each of the normal distribution with a different mean mu and a different variance sigma squared. It is because we can transform any normal random variable x to a standard normal random variable z by subtracting x with its mean mu and divide it by the standard deviation sigma. Then we can obtain a new random variable which follows standard normal distribution. So we can relate x with z and refer to the same table. For example, if we wish to find the probability that x is less than a, we can first rewrite it as the probability of x minus mu over sigma is less than a minus mu over sigma. Then it's the same as to find the probability that z is less than a minus mu over sigma, which is equal to phi of a minus mu over sigma. And we can make use of the table again. Please refer to the following examples by yourself. In the last video, we discussed the log-normal random variable. A difference between the log-normal distribution and a normal distribution is that it is not possible for a log-normal random variable to take negative value, whereas it is possible for a normal random variable to have negative values. It is not good to use normal distribution to model stock price because it has a negative side and stock prices cannot fall below 0. Instead, the log-normal random variable is very useful for analyzing stock prices. The following is how we model the stock price by log-normal distribution. Let S0 be the selling price of the stock on the present day and S1 be the selling price of the stock on the next day. We denote X as the ratio S1 to S0. It is more appropriate to model X by using log-normal distribution. If the stock price on the next day is higher, then X has a value greater than 1 and vice versa. Now let us refer to the following example. The ratio of the selling price of a certain stock on consecutive days is a log-normally distributed random variable with drift mu equals to 0.05 and volatility sigma equals to 0.2. We wish to find the probability that the selling price of the stock on the present day is less than the selling price on the next day. We denote X as the ratio of the selling price of the stock on the next day to the selling price of the stock on the present day. Then, according to the given information, X follows log-normal distribution with drift 0.05 and volatility 0.2. That means log X will be normally distributed with mean 0.05 and variance 0.2 squared. We would like to find the probability that the selling price of the stock on the present day is less than the selling price on the next day. That is, to find the probability that the ratio X is greater than 1. Therefore, we wish to find the probability that log of X is greater than 0. If we denote Y as log of X, then y is normally distributed with mean 0.05 and variance 0.04. We can relate y with the standard normal random variable z using this formula. Then the probability that y is greater than 0 is the same as the probability that z is greater than negative mu over sigma. Due to the symmetry of the standard normal distribution, the probability that z is greater than negative mu over sigma is equal to the probability that z is less than mu over sigma, which is equal to phi of mu over sigma, and it is equal to phi of 0.25 in our case. By referring to the table of cumulative distribution function for the standard normal random variable, we get the value 0.5987. The following is the table of the cumulative distribution function for the standard normal random variable.